Hello everyone. Today we're going to learn chapter 2 of the HLS book. In this chapter, we'll learn how to implement a finite impulse response filter. Today's learning objective is to understand the computation pattern of finite impulse response or FIR filter and make a working synthesizable HLS code for FIR. Then we'll run C and RTL simulation of your FIR code on Vitis HLS GUI and analyze the performance of the HLS design. FIR filter is one of the most widely used applications in digital signal processing domain. It is typically used for signal restoration and signal separation. For example, you could do a low-pass filtering to get rid of high-frequency signal and only obtain low-frequency signal. And as you can see on the equation, FIR filter does a convolution of the coefficients h and the input signal x and generates output signal y. And you can see in the example circuit when the number of taps is 4. I'll explain this circuit in more details with another example in the next slide. Let's take a look at this specific type of FIR filter, the moving average filter. It'll compute an average of past n samples. For example, if n is 3 and we're on I equals 12 sample, the y is going to be an average of past 3x samples. So we're going to multiply 1 over 3 on these 3 samples and add them together. Let's take a look at the hardware diagram. At each cycle, the value of x gets shifted to the right. This is called a shift register. And at each cycle, the value of x gets multiplied to the coefficients and added together. All the multiplication and the addition are being done in a single cycle. You can see that the multipliers and the adders are fully working in parallel, so FIR filter maps quite well to a hardware circuit. Now, let's try to implement this on HLS. This is the basic HLS code for the FIR filter. This part of the code goes after this part of the code. First, you can see that this is an 11 taps filter, and this code uses type def to make it easier to change types. But for now, you can think that all the variables are int type. Let's first try to make a shift register. In this line of code, you're copying the shift register 9 to 10. I is 10 in the first iteration. Then copying register 8 to 9 when I equals 9. 7 to 8, 6 to 7, all the way down to 0 to 1. At I equals 0, you're getting the input x in a separate if clause. Next, let's try to do the multiplication and the addition. You're multiplying the value of the shift register and the coefficients for each tab and accumulating into the ACC variable. And this is done in a separate clause when I equals 0. The final accumulated value will be written to the y output, and the function ends. Does everything make sense? All right, so now this code will operate correctly, but may not have the best performance. To analyze the performance, let's first try to synthesize this code on Vitis HLS. To synthesize the FIR code, we need to launch the Vitis HLS tool. There are two ways to launch the Vitis HLS. The first one is the command line mode. We'll be typing the commands in text in this mode, and it's similar to the method we use to synthesize the Hello World project. The second method is the GUI mode. I think most people will find this flow easier, so I'll explain it in the next slide. Just letting you know, I will be providing more details on different execution modes of Vitis HLS a couple lectures later. So if you want, you may jump a few lectures forward to find out more. Otherwise, let's see how to invoke the Vitis HLS GUI mode. In order to use the GUI mode, please make sure that you're accessing the AWS server that is nearest to you. Otherwise, the server response time might become unbearable. There are two ways to use the GUI interface. The first way is to use X. On AWS, you need to install relevant packages using yum install, and then you can set the environment variable display. On your PC, please make sure that you enable X11 forwarding on PuTTY, and also you'll need to install X Windows Server like Xmin. The second method is to use NICE DCV. You can use your web browser for access. If you have a school server with Vitis, you probably want to use the first method. But for AWS engineers are recommending the NICE DCV flow. So I'll briefly explain how to go for the second one. To install NICE DCV, please follow the steps on this website. It's pretty easy to follow. Let me just go over a few steps that might be a little complicated. In step 1, you need to set IAM role and policy. To do this, please right-click on your instance, go to Security, and click on Modify IAM role. In the screen, you'll find a button for creating a new IAM role. Click on that button. You'll be asked for the name of a new policy and a role. You can give any name you want, and then you'll be asked to specify your policy. You can switch to the JSON format and copy and paste the content that was in the AWS DCV website and replace the region to the region where you're accessing. In step 2, you can open up a TCP port of your instance by clicking on the Security tab and clicking on the item in the Security group. After clicking the item, you'll see Edit Inbound Rules button. There you see that it currently allows SSH to access port 22 only. Let's allow access to TCP port 8443 for NICE DCP access. Click on Add Role, Custom TCP, and port 8443. Please do not overwrite SSH port 22 because you will lose access to SSH connection. Then click on Save Rules. There are further steps in the AWS DCP website. Please go ahead and do as it says. It should be pretty easy to follow. If you're done with the configuring DCV, you can access it with any browser. Type HTTPS is your instance IP colon 8443. After you gain access, please go to the application and launch terminal. The terminal screen should be almost the same as your SSH console. In your terminal, please source the necessary files as usual, and then you should source the setting file for the Vitis HLS. And now you're ready to use the Vitis HLS GUI mode. Please type Vitis _HLS, and it'll bring a GUI screen for your Vitis HLS. Then please press the Create Project button. Now let's import the FIR source files. The authors of the HLS book have generously posted test code on their website. You can download it from this address. Then please copy and paste figure 2.1 code from our textbook into the FIR function. After copying the files to your working directory in AWS, please add the files into the Vitis HLS project. The top function name should be FIR. The design file should be FIR.cpp, and the test bench file should be FIR_test.cpp. In the configuration screen, set the clock period to 4 nanoseconds and the uncertainty to 1.08 seconds. This means that your FPGA kernel is going to run at the frequency of 250 megahertz. But the actual clock may arrive at a slight different timing at different registers up to 1.08 nanoseconds. For your part selection, you can leave it as the default selection. You may also change to the part name shown here. Well, to be exact, this part is the one that's being used by the AWS F1 instance, but it doesn't make too much difference to use the default selection. Now you have made your first Vitis HLS project. But before we do anything, let's check if we have copied and pasted the FIR code correctly from the textbook. Please click on the pull-down menu besides the green arrow button and click on the C simulation. This will compile your design with GCC and run C simulation. If the code has been copied correctly, you get the message, the output matches the golden output. Then you're good to go. But if you do not get such a message, it means that there are some problems. Please try to fix all the typos and rerun the C simulation. But even if you fix all the syntax errors, it is possible that there are still some problems in your code. In this case, you can use the Vitis HLS Debugger to isolate the issue. To do so, please click on the Launch Debugger option when you run the C simulation. When you click on OK, you get the debugging window. The interface should be similar to existing debuggers. You can set the breakpoints, step into, step over, or watch the content of some variables. If you run the debugger, you might find that the file read and the write routines in the FIR test CPP causes segmentation fault. In this case, please correct the file path to an absolute path, and then you should be good to go. If your C simulation passed successfully, please click on the green arrow button to synthesize your source files. Or you can also click on the pull-down menu and click on C synthesis. This process will create RTL files from your kernel source file. Now keep in mind that this is a standalone Vitis HLS synthesis, and it will not do placement and routing or create a FPGA bitstream like the regular Vitis flow we did for the Hello World project. This flow just synthesize your C source file and create the RTL output files. So if you wait a few seconds after clicking Save Synthesis, Vitis HLS will finish and generate a synthesis report. Before we look at the synthesis report, let's first talk about which metric we're going to use to measure the performance. One of the most commonly used metric is the execution time, and the unit is seconds. But since we're dealing with the synchronous digital circuits, it's often more convenient to talk about the execution time in the unit of clock cycles. As you know, the execution time in seconds equals to the clock cycle times the clock period. And this equals to clock cycles divided by clock frequency. The default clock frequency in AWS F1 is 250 MHz. This frequency is normal. The clock frequency in CPUs might be in the range of few gigahertz, but in FPGAs, it is often in the range of few hundred megahertz. Now, keeping this equation in mind, let's look at the synthesis report. The Vitis HLS synthesis report will pop up after you synthesize the design. What this report is saying is that it takes 27 cycles or 108 nanoseconds, since the clock period is 4, to finish the execution of one function call of FIR. In addition, it takes 1 cycle to call a function, so the initiation interval of a function is 28 cycles. If you look at the test bench file, FIR test.cpp, there are 600 samples and there are 600 calls of the FIR function. So in total, it is going to take 600 times 28 or 16,800 cycles to complete the overall execution. But ideally, it should take only about 600 cycles to process 600 samples, not 16,800 cycles, right? So we can see that the baseline performance isn't very satisfactory. We're going to learn how to optimize this design in the next class. But for now, let's try to confirm that our calculation of the overall cycles is correct. So to do this, let's run something called a co-simulation. Vitis HLS Co-simulation performs C simulation for the test bench file and the RTL simulation for the kernel file. It is useful because RTL simulation is almost cycle accurate, and we can get an accurate performance estimation. In addition, we can see waveform for debugging purpose. In order to run co-simulation, click on the co-simulation in the pull-down menu. Next, you have an option of viewing the waveform in the co-sim. You can leave dump trace as none if you don't want to see the waveform. But this time, let's change the dump trace to all and click on OK to run the co-sim. When the co-sim is done, it will tell you the execution time. The latency number should be 27, and the II of the function call should be 28, which is the same as the synthesis report. Now, there are some applications where the co-sim cycle number and synthesis report cycle number is different. We'll talk about such applications in later chapters. Now, let's look at the waveform generated in co-sim. Please click on this icon after the co-sim is done. When the loading is finished, please click on module FIR and look for signals named AP start, Y, X, and AP done. Then right click on these signals and add signals. AP start going to 1 is the cycle when the kernel starts execution, and the AP done being asserted is the cycle when kernel ends execution. There are 600 calls of the FIR function, so AP done should pop up 600 times. And if you count the number of cycles between when AP starts goes to 1 and the last assertion of AP done, the execution time should be 67.2 microseconds, or 16,800 cycles. This is the same number we calculated with the synthesis report, and this confirms that our calculation is correct. Now note that this waveform is also ideal for debugging purpose, and we're going to talk more about that in later lectures. In today's class, we have seen our first fully working and synthesizable HLS code for FIR filter. The FIR filter was composed of multiply, add, and registers. We also enabled the Vitis HLS GUI interface for FIR synthesis and simulation using Amazon's NICE DCV. For simulation, we did CSIM and the Co-sim. The C simulation is used to quickly verify the correctness of a design, and Co-sim enables waveform viewing and allows us to obtain psycho-accurate result. We also learned that the performance can be expressed in seconds or cycles. And that's it for now. In the next class, we're going to optimize our baseline FIR filter code and improve the performance. So I'll see you in the next class.